So if we go back to where we were on Friday we were looking at uh, kind of closing out our discussion of some types of reactions. And we picked on, at the very end, double replacement reactions, where we had some different kind of classes or subclasses of double replacement, like acid-base reactions, which will always give us water and a salt as products. And we went through this kind of quickly, but we talked about the different kinds of common acids and bases. How do we tell an acid or a base by formula? Acids start with hydrogen, bases end with hydroxides. That's kind of the way that we can tell an acid or base. If we were just given the chemical formula, we would look for one of those two things. And then we also talked about gas evolution, where I put a couple of things together and a gas forms as a byproduct. And the thing about each of these gases is that they have some kind of characteristic to them that is noticeable. So hydrogen sulfide gas has a rotten egg smell. Carbon dioxide, when it forms as a product, is very bubbly. Think your baking soda volcano kind of reaction. That level of gas generation is carbon dioxide through and through. Sulfur dioxide has an odor of burning hair or rubber, very strong, powerful kind of scent to it. And then ammonia has the odor of a cleaning agent, cleaner. Ammonia solvents are common in certain kinds of household cleaners. Depending upon what kind of window cleaner you buy, some versions of Windex use ammonia, some use vinegar, some use ammonium-based surfactants. You just read the label; it will tell you what it is. The one that is ammonia-based obviously smells like ammonia. But you would recognize, if you don't know what ammonia smells like, there's a chance that if I gave you a sample of ammonia, you could probably go, oh yeah, I've smelled this before. I just didn't know what it was. Now, the last class of reactions that we did not get a chance to talk about on Friday were this broad class of reactions called oxidation reduction reactions, or redox reactions. This umbrella class is kind of a catch-all for any kind of reaction that would involve moving electrons in a chemical reaction. And so if you look at some of the classes of reactions that are there, what you'll see is that combination reactions, they often are redox reactions as well. Decomposition reactions, they're often redox reactions as well. Single replacement reactions, those are really actually easy to see that they're redox because, well, you start with something that has no charge and it ends up having charge at the end of the reaction. Well, to go from no charge to charge, electrons had to be dealt in one direction or another. Combustion reactions are another one of those subcategories. But if we're just trying to kind of figure out, well, what is a redox reaction versus not a redox reaction, there are some characteristic things that we can look for. Those characteristic things are these three. If we see a substance reacting with elemental oxygen, that is a dead giveaway that I'm talking about a redox reaction. When things react with elemental oxygen, the elemental oxygen grabs electrons from them. Oxygen itself is something called electronegative. Electronegative elements will grab electrons from whatever they react with to bring more electrons to the oxygen in this case. So anytime anything reacts with elemental oxygen, that oxygen is stripping its electrons off of that other substance and turning it into some kind of either a positive ion or at least an element that has the tendencies of something that is electron deficient. So that's one telltale sign. Another telltale sign is when we have metals reacting with nonmetals. Now we know from our studies of the periodic table that metals tend to form positive ions and that nonmetals tend to form negative ions. Well, if I'm starting from no charge to positive and negative ions, I know that electrons have moved around. In particular, they have moved from the metal to the nonmetal. And then just more generally speaking, if I see changes in charge, I know that a redox reaction has taken place. So if I see that an element has gone from having no charge to having a positive 2 charge, well, to go from no charge to positive 2, you had to lose electrons along the way. If you lost electrons, that meant those electrons had to go somewhere. But even more subtly, if I have a reaction where a iron 2 ion turns into an iron 3 ion, it has changed charges from positive 2 to positive 3. That change in charge is a sign of redox. Any change in charge is a sign of redox. And so that's why with redox reactions, we tend not to put them into a single category, but rather we just kind of treat them all under this big umbrella of electron transfer. And so if you look for those 3 indications, that can help you to just casually look at a chemical equation and go, oh yeah, I can see it. I can see where the electrons have moved around here. This is redox. Or, you know what? It doesn't look like anything changed from a charge standpoint. I don't think this is redox. A real common example of this, not redox, double displacement reaction. Double displacement reactions are rarely redox because all that we're doing is changing ionic partners. And in changing ionic partners, usually we don't see a movement of electrons. We just see a redistribution of the existing ions to make new products. Now, hidden in this group of redox reactions is the 5th most common type of reaction, the combustion reaction. Combustion reactions are redox reactions. They have probably the most common telltale sign of redox in that they are a reaction of something with elemental oxygen. Now, the most common types of combustion reactions that we will focus on are the combustion of hydrocarbons, organic fuel materials. And in those cases, what we will see is that water and carbon dioxide are the most common products of those kinds of reactions. So something to be on the lookout for as far as identifying combustion reactions is this. If I notice that carbon dioxide and water are my products, there's a really good chance I'm looking at a combustion reaction here. The reactions of hydrocarbons with oxygen to make carbon dioxide and water are really common telltale signs that a combustion reaction is taking place. The other thing that we'll always notice is that combustion reactions are always exothermic. Now, this shouldn't be any kind of surprise to you. Combustion reactions generate fire. Fire is hot. But nonetheless, that is a common characteristic. So we always will be on the lookout. If I see a combustion reaction of any kind, I'm going to see a generation of heat. I'm going to see a generation of light. And depending upon what is burning, if it's a hydrocarbon, I'll see carbon dioxide and water. If it's not a hydrocarbon, I'll see some kind of oxygen product that comes off. Whether it's a metallic product, so like if I burn magnesium, I'm going to get magnesium oxide. If I burn calcium, I'm going to get calcium oxide. If I burn methane, I'm going to get carbon dioxide and water because methane is a hydrocarbon. Hydrocarbons, we're just talking about compounds that are made up of carbon and hydrogen. And sometimes oxygen too. So this would cover things like burning sugar, burning alcohol, which are common combustion reactions as well. So that is the stuff that we were covering largely last week. And I know we didn't get all the way to combustion reactions on Friday. But if you haven't done assignment 7-1 yet, classifying reactions, that's all that you're being asked to do. Classify the reaction, get a chemical reaction. What is it? Is it single displacement, double displacement, combustion, combination? What is it? Today we're talking about chemical equations from a different standpoint. And what we want to look at in this particular viewpoint is going beyond what we were looking at last week. So this is kind of what we did last week. We have reactants, we have products. We can, with the information that we pulled in at the end of last week, we can look at this chemical equation here on the bottom and say, oh, this is a combustion reaction because I've got a hydrocarbon reacting with oxygen to make carbon dioxide and water. I can also look at this reaction and say, okay, this is a gas phase reaction. All of the reactants and all of the products are in the gas phase. And since this is a combustion reaction, I would expect it to be exothermic, to generate heat. But we want to go beyond just this kind of characterization. We want to talk about this chemical reaction a little bit more precisely, a little bit more finely. So what else can we say? What else can we do with this? Well, one of the things that we can do is we can start to look at this reaction more from a perspective of, well, what's going on at the molecular level? So at the molecular level, I can see that I've got one molecule of methane, CH4. I've got one molecule of oxygen, O2. And I've got one molecule of carbon dioxide, CO2. and 1 molecule of water, H2O. But one of the things that I'm going to point out here that is problematic is, well, hold on. I've got 1 carbon on each side, so that makes sense. I've got 4 hydrogens in this methane, but I only have 2 hydrogens in this water molecule. That doesn't seem right. And I've got 2 oxygen atoms in this oxygen molecule. If I look at my products, I see 3 oxygen atoms overall. A couple of weeks ago, we made mention of the idea of the law of conservation of matter. And right now, it doesn't seem that the equation that we wrote is obeying that law. Law of conservation of matter says that matter cannot be created or destroyed, and yet this equation, as we have it right now, is doing both. We've somehow destroyed 2 we somehow have destroyed 2 atoms of hydrogen, and we somehow created 1 atom of oxygen. So something is amiss here. Something does not quite make sense. The equation that we have written is accurately portraying the chemical reaction and the substances involved in that reaction. But yet the chemical reaction that we've written is also violating the law of conservation. Now, how do we go about fixing this? Well, the answer to that question is we've got to create a balanced chemical equation. We've got to obey the law of conservation. Now, there are 2 approaches that we could take to obeying this law of conservation. One of them would be that we just manipulate the chemical formulas to get it to work. So I take CH4 and I say, okay, well, maybe that's just CH2, and I change carbon dioxide into carbon monoxide, and now I've got a balanced chemical equation. Problem is that doesn't work. And the reason it doesn't work is because we know that changing the chemical formula of something also changes its chemical identity, also changes its properties. Carbon dioxide is a byproduct of cellular respiration. You are generating carbon dioxide every second of your life. You're breathing carbon dioxide in and out every second of your life. If I change that carbon dioxide to carbon monoxide, you will soon die. Because carbon monoxide is not the same thing as carbon dioxide. The carbon monoxide will block your hemoglobin from transporting oxygen. And without oxygen, you can't do that cellular respiration, and you can't do any of your other bodily functions. You will literally die from that exposure. So we can't do it this way. We can't do it from the perspective of let's just change the chemical formulas. So we have to have another approach to take. And that other approach to take is instead of changing the formulas, why don't we change the ratio of the substances? So instead of talking about carbon monoxide as a possible product instead of carbon dioxide, what if we look at how many molecules are actually involved? So in this particular case, if we look at this reaction as having 2 molecules of oxygen instead of just 1, 2 molecules of water instead of just 1, now we've maintained the integrity of the substances themselves by preserving them. But we've also created a method that is going to allow the law of conservation to exist. I still have 1 carbon on each side. I now have 4 hydrogens here in this methane molecule and 4 hydrogen atoms in these water molecules, so we now have equal numbers of hydrogen. I have 4 oxygen atoms in these 2 molecules. And I look at all of my products, I see 4 atoms of oxygen across those products. The law of conservation is being upheld here. By looking at the number of molecules of each substance rather than the substance's chemical formula. So this is why we have to focus on the idea of balancing chemical equations. When we start looking at chemical reactions and going just beyond what happened. Because if we want to do anything with these chemical equations and with these chemical reactions, in terms of predicting what is going to take place, or calculating how much reactant or product to measure out, or predicting how much product is going to be there when we do the reaction itself, we need to be able to look at things and say, everything is balanced. We are behaving according to the law of conservation of matter. And that's why balanced chemical equations exist and why they need to exist. So this generic equation just kind of tells you how to set it up. We are going to use coefficients in front of the chemical formulas to help us with the balancing act, as opposed to playing around with the chemical formulas themselves. Now, not every chemical equation is going to follow this particular format, where there are 2 reactants and 2 products and that kind of thing. Again, this is just a generic kind of setup. We would use this same setup for any number of reactants and any number of products. But the important thing to know out of it is that the coefficients are what we change to help us get to the balancing, to help us to get to the law of conservation there that we're trying to meet. The question becomes, well, how do we do it? How do we go from this raw chemical equation that is unbalanced to a chemical equation that actually is balanced? And in your notes here, I'm trying to give you a methodology here. The atom economy method that I'm describing here, this is an organizational system. This is a way to kind of help you to figure out what you have in the chemical equation currently and how to get to that balanced chemical equation at the end. It's a relatively simple setup. You split the reaction into reactants and products, and you just count. Okay, I've got oxygen and nitrogen, and on this side of the equation, there are 5 oxygens and 4 nitrogens, and on this side of the equation, there are 2 oxygens and 1 nitrogen. This accounting lets you know when your elements are balanced or not balanced. And obviously, if they're not balanced, then that's when we do something about it. That's when we play around with the coefficients to try to get them to balance out. As you make changes to the coefficients, you mark out those changes in the atom economy, in the organization, and you keep working until everything is even on both sides of the equation. Now, some things to look for, things that could help us to make this a little bit easier. In displacement reactions, A lot of times we are going to be dealing with polyatomic ions, things like nitrate ion or chlorate ion or cyanide ion or you name it. Instead of breaking those ions apart into their individual pieces, it's actually a lot easier to track them as a whole, as a cluster. So if I look on both sides of the equation, I see the nitrate is on both sides. Instead of marking nitrogens and oxygens, I should mark nitrates because it'll be a lot easier to keep that all together. The second tip, and this is a really common one, if there are compounds that have multiple subscripts, chances are pretty good those subscripts are going to drive the equation balancing on the other side of the reaction. The last thing, if all else fails, do your balancing in order of complexity. Start with the least complex and move to the most complex element. Now, how do you evaluate complexity? How many substances is that element in? So the simplest would be that you have an element that is in one compound on each side. The most complex would be something like oxygen. Oxygen loves to do this, where it's in every compound on both the reactant and the product side. What we hope for in this kind of situation, what we hope for is that by the time you get to that most complex element, everything else has kind of worked itself out. And you either have a very simple manipulation to make, or it's already balanced itself out and you don't even need to handle the last one at all. So let's take a look at some example problems. I'm going to start with a first example here. Now, if you're following along in the notes, there are a series of slides where the next step is just loaded on and you see it piece by piece by piece by piece. If you're just writing as you go here, just start here and add as we go. But the reaction is this. We are reacting nitrogen dioxide gas with water to make nitric acid and nitrogen monoxide. So the first step is this. If I don't have the chemical formulas already written down, I need to write them down in an unbalanced equation like this. So nitrogen dioxide is NO2, water is H2O, nitric acid is HNO3, nitrogen monoxide is NO. If I don't have that information, I need to use my nomenclature skills to give me the correct chemical formulas before I can start to try to balance it out. Now, in a lot of cases, you'll already be given this skeleton reaction where everything's already here. And if that is the case, then the first thing that you do is you organize your reaction. So draw a line between the reactants and products and start doing an inventory. This element, this reaction has nitrogen, oxygen, and hydrogen in it. And now I'm just going to count out each side. I've got one nitrogen on this side. I've got 1 and 1. So a total of 2 nitrogens over here. For oxygen, I have 2 and 1 for a total of 3. On this side, I have 3 and 1 for a total of 4. And for hydrogen, I have 2 on this side and 1 on this side. So When we talk about atom economy or organization, this is what we're talking about. I've taken this chemical equation, I've broken it down into each individual element, and now I'm comparing each element against each other. And my first evaluation here is that nothing is balanced. I don't have equal numbers of nitrogen on either side, oxygen on either side, or hydrogen on either side. So that is my step one. My step one is write out the chemical formulas if they're not given to me. And if they are, or if I've done that step, then take my first inventory. And so we can see, again, none of these are balanced as is. Now comes the question of how do we start to balance it out? Where do we start? What element should we look at? And this is where we have to evaluate complexity. From a complexity standpoint, I can see that nitrogen, I'll highlight it in orange, nitrogen is in 3 of my molecules. Oxygen is in all 4. And hydrogen is only in these 2. So from a standpoint of complexity, hydrogen would be the least complex because it's in the fewest molecules. Nitrogen is the next, it's in 3 of the 4. Oxygen is the most complex, it's in 4 of 4. So we're going to try to leave oxygen for the very end. So working in order of complexity, or least complex to most complex, I would want to start with the hydrogen because the hydrogen is the least impacted. And I look at this and say, okay, if I have 2 hydrogens over here, I need 2 hydrogens over here. Well, to get 2 hydrogens, I would need 2 nitric acids. Now, the thing is, when I put this coefficient in front, not only am I changing the hydrogens, I went from 1 hydrogen to 2. But I'm also changing the nitrogen and the oxygen as well. Because nitrogen, I now have 2 times 1, so 2 plus an additional 1, this is now 3. And for the oxygen, I have 2 times 3, which is 6, plus 1 more, that's 7. So I've balanced out the hydrogen, but it has not balanced out the oxygen or the nitrogen, at least not yet. So we've made our first move. Our first move was to balance out the hydrogen because it was the least complex. We did that. It manipulated the nitrogen and oxygen. We calculated those adjustments and put them into our bookkeeping here so that we are still working off of fresh, new, the best data. Now we've got nitrogen and oxygen. And for that, again, we're still working off of complexity order. Nitrogen is still in fewer things than oxygen is. So let's try to balance out the nitrogen next. And if I do that, I see, okay, I've got 3 nitrogens on this side, but only 1 nitrogen on this side. If I triple the amount of nitrogen dioxide, that'll change me to 3 nitrogens. But it'll also change the oxygens. Oxygens will go 3 times 2, that's 6, plus 1 more, that's 7. And as it turns out, we got exactly what we were hoping. In balancing out the nitrogen, we have accidentally balanced out the oxygen as well. I don't need to do anything further. All 3 of my elements are now perfectly balanced. I'm done. And that's why we do this particular technique with the atom economy, bookkeeping kind of technique. Now, as a warning and a caution, I will tell you this. As you practice and get better, you are going to need to do this less and less. Because at some point you will hit a mark where you just kind of understand, okay, I can see from this equation that this is what needs to happen, and I need a 2 over here, and I can kind of look and do it in my head and see that I need a 3 over here. That's called balancing by inspection. It is a skill that is learned. It is a skill that you just pick up as you get more practiced. But until you get to that point, this is the way to keep you organized and give you a definitive, yes, the equation is balanced because I can see that all my elements are even. They're all balanced out, they're all equal. Now you can always check yourself and look at, okay, can I count everything up again and make sure? So I got 3 nitrogens over here. I got 2 plus 1, that's 3 nitrogens over here, that balances. 3 times 2 is 6, plus 1 more is 7. So I got 7 oxygens here. 2 times 3 is 6, plus 1 is 7. So those are balanced. 2 hydrogens, 2 times 1 is 2. All my elements are balanced. I'm in good shape. For some kind of redox reactions, keeping track of charge is important as well. That's not something that we're going to focus on a ton in this class. That's something more down the line. When you get into general chemistry, you'll see more of that kind of stuff. Let's take a look at another practice problem though. Here we have a combustion reaction, C8H18 reacting with oxygen to make carbon dioxide and water. Again, one of the things that you need to kind of start to think about when you're looking at chemical reactions, can you classify them? Can you look for those telltale signs? I have hydrocarbon, carbon and hydrogen molecule together, reacting with oxygen to make carbon dioxide and water. Carbon dioxide and water, very common products for combustion reaction. So I've got my unbalanced equation. That was part 1. I need to split it into its elements. I have 8 carbons over here, but just 1 over here. 18 hydrogens on the reactant side, but just 2 on the product side. 2 oxygens over here on the reactant side. 2 plus 1 is 3 on the product side. Just like last time, we have a equation that does not balance in any of the elements, at least initially, but that's okay. One thing we do have is we do have a compound that has multiple subscripts. Now, why is that important? Because if I have multiple subscripts, those subscripts can drive the equation balancing on the other side. The only place where carbon exists is in carbon dioxide. The only place where hydrogen exists is in water. So if I can get these numbers to match these subscripts, I have a good idea of what my coefficient should be. So I need 8 carbons That's going to be 8 carbon dioxides. I need 18 hydrogens. That's going to be 9 waters, because 9 times 2 is 18. I just manipulated 2 coefficients. I need to make sure that my math works out. So 8 times 1 for carbon is 8. 9 times 2 is 18 for hydrogen. For the oxygen, I have 8 times 2, that's 16, plus an additional 9 times 1 is 9. There are 25 oxygens on the product side of the reaction. Now, this is where we're going to run into a little bit of trouble. Because the only thing left to balance is the oxygen. And I need 25 oxygens on this side of the equation. But every oxygen molecule gives me 2. So how do I make an odd number out of evens? Now, the answer that I tell my Chem 105 students is we cheat. I put a fraction in here, 25 over 2. And since 25 over 2 times 2 is 25, I've got me a balanced chemical equation. As you might guess, this particular approach is a little bit problematic. Because if we're talking about oxygen molecules, O2, how do I get half of one of these? I don't know, and neither do you. That's the problem with this particular approach. So if we find ourselves in a situation where the only way to balance it out is that I have to put a fraction or a decimal in here, and I'll be honest, the fraction or decimal is always 0.5. If that is the case, obviously that doesn't work. But the way to get around it, if I multiply every single one of these coefficients by 2, I will end up getting where I want to go. So now it's 2 octanes. And 25 times 2 is 25 oxygens. 2 times 8 is 16 carbon dioxides. And 2 times 9 is 18 waters. Does this work? Is it balanced? Well, let's do the math. 2 times 8 is 16. 2 times 18 is 36. 25 times 2 is 50. For the carbon, 16 times 1 is 16. For the hydrogen, 18 times 2 is 36. And for the oxygen, 16 times 2 is 32. And 18 times 1 is 18. Put 32 and 18 together, I get 50. So is this balanced? Well, I have 16 carbons on each side. I've got 36 hydrogens on each side. I've got 50 oxygens on each side. Yeah, it's balanced. Everything is matched up equally. And that's ultimately what we are looking for. Are we matching things up equally? So in these kinds of situations, that's exactly what we have to do. If I find myself needing a fraction or a decimal to get it to balance, I multiply by the denominator of that fraction, which again is usually 2, to get it all to even out and come out just right. All right, questions in this practice problem? I will tell you, combustion reactions are probably the hardest to balance because that's where this particular thing happens the most often. Right. I'm going to skip this. The answer to it will be in the notes. But I want to move on to this Pear Deck question. We'll do it together, but I do want you to be able to enter it into the record and get your point for it. So we are looking at slide 3 here in Pear Deck. We're asked to balance this equation and to put in the coefficients as just a 3-digit code. So if we set up our organization here, I have 2 nitrogens and 5 oxygens on the reactant side. I have 2 nitrogens and 2 oxygens on the product side. What we run into is the same exact problem that we just talked about. Nitrogen is even to a piece. Oxygen is not. And I have no way of getting the oxygen to match up without using a fraction. So to get what I want, I need 2.5 oxygens. 2.5 times 2 would give me the 5 that I need. But the problem is, again, from a molecular standpoint, there's no such thing as half of a molecule. So in the circumstance, what do? The same thing. We multiply everything by 2. And so with everything multiplied by 2, I would have 2 dinitrogen pentoxides, 2 nitrogen molecules, and 5 oxygen molecules. If I do the math on that, 2 times 2 is 4, 2 times 5 is 10. So I now have 4 nitrogen and 10 oxygen. On the product side, hopefully it's the same story. 2 times 2 is 4, so I have 4 nitrogens. That matches up. 5 times 2 is 10. I have 10 oxygens. That matches up as well. Everything matches. The equation is balanced. 225 would be the 3-digit code that you need to enter. So go into Pear Deck and enter that code. Also, go down to slide 6 and answer this question here about today's lesson. So on Friday, we are going to do a little bit more practice with balancing just to kind of round out what you saw in PLTL. And then we're going to get into discussing solubility rules and how to predict whether a reaction is going to form a precipitate or not form a precipitate based upon just the classifying the double replacement reaction and predicting the products. Have a good afternoon.